Hi there, and welcome to Papetti Math's YouTube channel, where I am going to teach you Algebra 1. We're going to continue with exercise number 4 in Lesson 4, Finding Zeros by Completing the Square. Now, in this lesson, we have just seen that in exercise number 3, by factoring a quadratic, we could arrive at the same answers as exercise number 2, where we completed the square to find the zeros. So whether we completed the square or factored to find the zeros, we arrived at the same solutions. But if we're looking at exercise number 4, it says, why is it essential to learn this new method of completing the square to find the zeros? This is because not all quadratics are able to be factored. For quadratics that cannot be factored, you will use the method of completing the square. Find the zeros of the quadratics below. So we're going to first look, and we're going to take a look if this can be factored. And you have 3 here. So you need two numbers that multiply to 3. And you might think to do, 3 and 1, that might give me a 4. So I'm going to try to factor this. I'll put x and x because x times x will give me x squared, and then 3 and 1. Now, how can I multiply to negative 3? Well, one of them has to be negative then. So I'll make the negative 3 and a positive 1, but those would combine to negative 2. So let me switch my signs here, and I'll put a positive 3 and a negative 1. But at the same time, this would multiply to negative 3, but it would combine to a positive 2. So there's no way to find two numbers that multiply to 3 and add to positive 4. It's not possible. So since this is not going to be an integer solution, what we want to do is we want to go to our next method that we're learning, which is completing the square. So our method for completing the square in part A says to move our c term to the other side. When we move our c term to the other side, we're going to have x squared plus 4x, remember to leave that space, is equal to 3. Our next step to complete the square is to divide the b term by 2 and square it. So 4 divided by 2 is 2, and 2 squared is 4. So we're going to add 4 to both sides. Now we're going to factor the left. That's a perfect square trinomial. And we're going to combine the right side. 3 plus 4 will give me 7. When I factor the left side, I need to look for two numbers that multiply to 4 and those same two numbers that add to 4. So this is a simple one. This is going to be 2 times 2 is 4, and 2 plus 2 is 4. So x plus 2 squared is the factored form of x squared plus 4x plus 4. Now we're looking to find the zeros here, so we're looking to solve for x. In order to solve for x, we need to get inside these parentheses. And to get inside these parentheses, we have to undo this squared right here. So to undo a square, we take the square root. Now, we're going to be left with x plus 2 on the left side. And on the right side, the square root of 7 can't be simplified any further because 7 is already prime. So the only thing we want to remember to do is remember to say that we know that there's going to be a positive and negative answer to our square root of 7. Our last step is going to be to subtract 2 from both sides to get x all alone by itself. We'll be left with x is equal to, I like to put the negative 2 first, negative 2 plus or minus the square root of 7. So these are actually the two exact values of the roots of the equation x squared plus 4x minus 3. If you were to put negative 2 plus the square root of 7 in your calculator, you'd get a very long irrational decimal. And this long irrational decimal is actually the exact precise location where this quadratic crosses the x-axis. And if you were to graph this quadratic and find the exact zeros on your graph, it would match negative 2 plus the square root of 7's value. Likewise, if you did negative 2 minus the square root of 7's value, that would be your second zero of this quadratic. So this quadratic has two zeros. One of them is located at negative 2 plus the square root of 7, and the other one is located at negative 2 minus the square root of 7. Let's take a look at part B. And in part B, we have x squared plus 6x minus 59. So we're going to look, and it doesn't look like we're going to be able to find two numbers that multiply to 59 and combine to 6. So what we're going to do instead is we're going to use our method of completing the square here to solve and find the zeros. So let's start by adding our c term to the other side because our c term is currently negative, so our inverse would be positive. And we're going to have x squared plus 6x, leave a space, is equal to 59. Our next step in completing the square is to take your b term, divide it by 2, then square it. So 6 divided by 2 is 3, and 3 squared is 9. So we're going to add 9 to both sides of our equation. By doing that, we have created a perfect square trinomial on the left side, which can be factored in this form. And when we add 59 plus 9, we'll get 68. So in order to factor, we're looking for two numbers that multiply to 9 and add to 6. And yes, you guessed it, 3 times 3 is 9, and 3 plus 3 is 6. And finally, to solve for this, we're going to take the square root of both sides to undo this squared so we could get in towards that x. We'll be left with x plus 3 is equal to, the square root of 68. So we're going to have to simplify the square root of 68. See if it can be simplified by making a prime factor tree. So what two numbers would multiply to the square root of 68? Well, it's an even number, so we'll start with 2. The square root of 2 times the square root of 34 will give me the square root of 68 when I multiply. 2 is prime, so I'll circle it. And then 34 is the square root of 2 times the square root of 17. And both of those numbers are prime, so now I have my prime factorization. So going back to my problem over here, I want to take a look and see if I have any pairs. I have a pair of 2s, so I'll cross off 2 2s, and I'll write 1 2 on the outside. And I have a single 17, so I'll cross off the single 17 and write 1 17 on the inside. Don't forget my plus or minus. And so square root of 68 simplified is the same as 2 radical 17, plus or minus. So my last step then to get x by itself would be to subtract 3 on both sides of my equation, and I will have left x equals negative 3 plus or minus 2 radical 17. So again, this is the two exact values of the roots of this quadratic. If you did it any other way, you'd have rounded answers because you'd have to stop your decimal somewhere because your decimal was irrational. So this is why using the method of completing the square is very useful for finding the zeros, because you can find that exact value by simplifying your square roots.